Software optimization is one of the measures to reduce overall energy consumption by the computer. Software optimization techniques can focus on the code, data, and resource usage. Code can be optimized by improving efficiency of algorithm, reducing complexity of the software, and refactoring code for faster execution. Data can be optimized by adjusting database and data structures layout, ensuring efficient data retrieval. Resource usage can be optimized with proper cache and memory usage, reducing unnecessary data transfers. It is recommended to use specialized tools to identify bottlenecks in the code of resources. We'll discuss optimization from assembler language perspective. Optimization strongly depends on the microarchitecture of the processor installed in a system. Some optimization recommendations change together with the new versions of processors. Producers usually publish the most up-to-date recommendations for programmers on how to write programs which properly use the newly implemented processor features and mechanisms, and what should be avoided. Sometimes it touches some specific instruction, which are recommended for use in one architecture and should be avoided in others. In this video, we'll present just a few examples. It is recommended to place variable in the memory at their natural boundaries. It means that if a data is 16 bytes, the address should be evenly divisible by 16. For 8-byte data, the address should be divisible by 8. It is recommended to use registers instead of memory for scalar data if only possible. Keeping data in registers eliminates the need to load and store data in the memory. It is natural for programmers to use ints or dets instructions to increment and decrement the variable. These instructions are simple and appear to be executed faster than addition and subtraction with a constant of 1. The ints and dets are single-byte instructions, while add and sub with the argument as a constant consume at least 1 byte more. But the problem with ints and dets instructions stems from the fact that they do not modify all flags, whereas add and sub modify all. Modifying all flags frees the processor from the need to wait for previously executed instructions to finish their operation in terms of flag modification. Intel recommends replacing ints and dets with add and sub instructions, but compilers do not always consider this recommendation. Similarly, in modern processors, new versions of other instructions were introduced which do not affect flags to reduce inter-instruction dependencies, if not required in the algorithm. Examples are shift and rotate instructions. Let's consider 3 logic XOR instructions: PXOR, XOR-PS, and XOR-PD. All of them can operate on 128-bit XMM registers, performing the bitwise logic XOR function. At first sight, the instruction choice is meaningless. The result will be the same. In reality, the selection of the instruction matters. The performance analysis yields a result that, in different situations, the execution time can be longer or shorter. A deep analysis reveals that when previous calculations are performed with integers, it is better to use integer operation PXOR. If the data is floating point, it is better to use floating point versions, XOR-P or XOR-PD. It is a common method to pause the program execution and wait for an event for a short period in a spin loop. In case of a brief waiting period, this method is more efficient than calling an operating system function, which waits for an event. In modern processors, the pause instruction should be used inside such a loop. It helps the internal mechanism of the processor to allocate hardware resources temporarily to another logical processor. In modern microarchitectures, the cache memory is essential for improving performance. In general, the processor handles cache memory in the most efficient way possible. However, it is easy to write a program that prevents the processor from utilizing this mechanism efficiently. The cache works on two main principles: temporal locality and spatial locality. The term temporal locality refers to the fact that if a program recently used a certain portion of data, it is likely to need it again soon. It means that if a data is used, it remains in the cache for a certain amount of time until other data is loaded into the cache. It is efficient to keep data in a cache instead of reloading it. The term spatial locality refers to whether a program has recently accessed the data at a particular address. Likely it will soon need the data at the next address. The cache helps the program run faster by automatically prefetching data and code that will likely to be used or executed soon. Some recommendations for efficient cache use are: the program should do as much work as possible on one small area of code and data. After doing the job, it can move to the next part. The program should avoid frequent jumping over distant regions of memory. While processing big multidimensional data arrays, keep in mind that their placement in memory, row-wise or column-wise, which is specific to the programming language. Object-oriented programming helps to utilize cache because members of the class are grouped. We already know that the cache temporal locality helps improve performance in situations where the program uses the same variable repeatedly, for example, in a loop. But if the processed data exceeds half of the size of the level 1 cache, it is recommended to use the non-temporal data move instructions to store data from registers to memory. These instructions are hints to the processor to omit the cache if only possible. It doesn't mean that the data is immediately stored directly in memory. It should be considered that the data can remain in the internal processor buffers, and likely the last version is not visible to other units of the computer. It is the programmer's responsibility to synchronize the data using the store fence instruction. In general, fence instructions guarantee that the load and store instructions before the fence are completed before executing and next instruction after the fence. Some instructions are hints to the processor indicating that the programmer expects the data to be stored in cache rather than in memory, or they do not expect to use the data in cache anymore. Prefetch is a hint to the processor, which indicates that the memory area should be considered higher in the hierarchy cache. CL-flash flashes a cache line from all levels of cache. Optimization is rather a complex but very interesting topic. Knowledge about the processor microarchitecture helps the programmer to write better, faster, and more energy-efficient software, not only in assembler language, but in any other programming language.